Hello AP Chemistry and welcome to titration. So here we do a way more thoughtful analysis on titration than we did in chapter 4. So really important, let's talk about things you should already know, right? So for example, we already talked about things like the equivalence point, right? And what happens at the equivalence point? Here we need to be really, really specific. Actually, yes, let's do that first. That's a great idea, right? We have our analyte and we have our titrant, because I'm sure that's what you were thinking, right? We have our analyte and our titrant, right? This is what we don't know, right? This is, and this is what we do know, right? So this is our known solution, and this is our unknown solution. Okay, so either we don't know something about it, right? And that something is going to tie back into moles. And we have our titrant, which is our known solution. Known? Or no? Yeah, we'll say known. And bearing those two things in mind, right, we have our equivalence point, right? And this is where, really specifically, right, the number of moles of titrant added equal the number of moles of analyte originally present. So, and you may wonder about the wording, right? Why does it have to be so specific? Why can't we just say moles of titrant equals moles of analyte? Because when you say things like that, right? And so here is where it's really important how we commit things to memory. If you're going to commit it to memory in a way that's going to be helpful to you, right? If you just say that the moles of titrant equals the moles of analyte, there is a strong probability that when we start talking about calculations at the equivalence point, you're going to say that, oh, the moles of titrant equals the moles of analyte, and you're going to start to assume that they're present, right? But the key here is that neither are present at the equivalence point, right? The number of moles of titrant added equal the number of moles of analyte originally present, and at the equivalence point, none are present. Okay? None of these are present at the, that says present. None of these are present at the equivalence point. Yes? Super important. All right? Now, the endpoint, right, which we talked about before, is hypothetically the same place as the equivalence point, right? The endpoint is our visual cue that we've reached the equivalence point as best our indicator lets us know, okay? And we know that the result is that we can figure out the moles of my analyte, which we can then use to find concentration or molar mass or molar mass and then maybe an empirical formula, right? Lots of things we can do starting from moles. All right, so these are things we already know, and we already know the basic setup, right? We have a burette, we have a flask, right? We have all that stuff. We already know, we've already talked about how down here in my flask, right, the amount of water added is irrelevant, right? Because what matters is that the number of moles down here don't get changed, right, as we wash down our flask. Remember all that? Fantastic, right? Remember when we talked about our burette, right? We talked about how this burette, right, it's really important that that concentration of our whatever we're using is known really, really exactly, which is why, going back to questions we had in that chapter, right, we don't rinse this with water, right? We rinse this with the titrant we're going to use, so there's no dilution of my concentration, okay? And don't forget that these are read top down, okay? All right. Now, here we have a titration. This is a titration curve, to be specific. Let's get a different color. So here we have a titration curve. Now, based on what this curve looks like, we should be able to discuss what kind of acid and what kind of base we're talking about. Okay. Now, a couple of things to take note of. Titration curves will always be pH on the y, and will always be mils. Well, it doesn't always have to be mils, but we'll usually have some reference to your standard or to your titrant down here, right? So this is information about our titrant, right? It can be milliliters, it can be something else. If we're using an automated kind of equipment, it could be time, right? If we're adding a constant number of drops per time, this could also be a time point down here, okay? And this is always going to be our pH. So here we see, right, this first point here is my pH when there are 0 mils of titrant added, right? Which means that this reflects just the concentration of my analyte, right? So if we look here at the blown up picture, right, this is a pH of 1, right? If I have a pH of 1, I'm talking about a strong acid, right? pH of 1, strong acid. And this is what it looks like, right? My strong acid is completely dissociated, and this governs my pH at that point on my graph. Yes? Okay. Then we have this point here where we get a very small rise in pH, because you'll see from 0 milliliters all the way to approximately, I don't know, what is that, 45 milliliters. From 0 to 45, we get a pH unit change of about 1. Yes? Do you see that? 1 pH unit change, okay? Which, obviously, in terms of our scales, is a 10-fold change in concentration. But in terms of our graph, that's only 1 pH unit change, which is very little, right? And that's one of the characteristic signs of a strong acid, strong base titration, is that this first part of the curve exhibits very little change in pH, okay? And if we think about that, my HCl is already completely dissociated, right? Which means that as long as there is a significant amount left, the pH is going to be decidedly acidic, right? So we are, on this part, neutralizing a little bit at a time, a little bit at a time, a little bit at a time, till we get here, right, wherein we reach our steep rise, okay? And this is indicative of our equivalence point. For a strong acid, strong base titration, this is always going to be a really steep, long rise, okay? For a strong acid, strong base titration, this is going to be a steep, long rise, okay? And you'll see that what that means is as we approach the equivalence point, right, from this point here to this point here is pretty much where the entire pH change happens, right, over the course of less than 10 milliliters, right? If we were being really specific, this giant rise happens over a window of maybe 1 milliliter, okay? Which is why, going back to our titrations, right, if you miss the endpoint by more than a drop, right, that's a huge change in your color, because all this pH change happens in that little space, okay? And that's where we go from being acidic to being basic. And why does it become basic up here? Right, because once we pass the equivalence point, we now have excess base, right? So at the equivalence point, like I said, we have neutralized completely our original strong acid, right? The moles of titrant, right? So if we think about here, right? The number of moles of hydroxide added, right, equal the number of moles of H plus originally present, right, none of which are present at the equivalence point, which means that here, in terms of species, what do we have? Right, we have sodium ions, we have chloride ions, and we have water. Yes? Does that make sense? Strong acid, strong base, all of these have been completely neutralized, and these are all that's left, right? Our leftover spectator ions and some water, which is why you'll see that this pH happens at 7, because it's reflecting the pH of pure water. Yes? And once we go the tiniest smidge past that, right, we start to get our excess sodium hydroxide, until eventually we reach our wherever we decide to be done, right? And this pH completely reflects sodium hydroxide, yes? Okay, please make sure all these points make sense, because we're going to do a weak acid titration curve next. So again, important points: slow rise in pH, long steep rise at the equivalence point, right? And over here, right? And again, you should know which species are present here, on the way here, here, and once we pass there. All right, next up.